existence, you have to introduce mixed strategies, but mixed strategies here play an important role. So I'm just ignoring it, although in the paper we do analyze this. So I want to talk about equilibrium with small solicitation cost. So I do a construction for the case that when the solicitation costs are small. So why small? For two reasons. This is the natural, maybe in some ways, it's a natural case for considering competitiveness and information aggregation, because if the cost is small, it means that there will be many participants, and then, of course, it's hard to expect that the price will be competitive and information will be aggregated if there are just a few bidders there. So you want many bidders. To have many bidders, it has to be that it can't be that the cost of solicitation are too low. So it's a natural assumption, but it's also the case that we know how to analyze. It's more difficult to come with sharp results for the case of large cost. So what do I mean by small cost? It's look at a sequence of S that goes to 0 over the sequence, and the sequence of corresponding, and the sequence of games that corresponding to it, and the sequence of equilibria of these games. You see, this is some leftover. It should be bold N, but this is really the notation that we use for the mixed strategy, because in fact we have to speak about mixed strategies, but here we're talking only about pure. So replace this with bold N. So a sequence of equilibria of these games, and all associated equilibrium magnitudes for the equilibrium, for the particular selected equilibrium will be indexed by K. So we are looking at a sequence of costs of solicitation and a sequence of games associated with it, and a sequence of equilibria associated with these games. So I want to construct for you a no aggregation equilibrium, and it will be pooling like in the above example that we saw a few minutes ago, and we'll show that such pooling can arise with optimal solicitation. So the special case that I will consider here is the case that I will call good news, bad news. There is a signal x hat in the interval such that the likelihood ratio is a step function. It's constant, smaller than 1 for x below x hat, and it's constant above 1 for x greater than x hat. So it's a continuum of signals, but for information perspectives, there are only two information contents. All the signals with x below x hat have the same information content. All the signals above x hat have, for the bidder, carry the same information content. And of course, the higher signals are more favorable than the lower ones. Now, we need also some technical assumptions that I will not explain. I'm just mentioning it. Ignore it. But there is some additional assumption I have to make in order to tell you this result that I'm going to tell you. So the result is, look at this sequence. So again, in words is, think of the situation when you make this solicitation cost small, and look at the corresponding games. The proposition says there exists a sequence of equilibria such that the solicitation, as the solicitation goes to 0, the solicitation itself increases, and for some b and k large enough, everybody with signal above x hat is bidding this b, and this b is smaller than the x ante expected cost. This is the x ante expected cost. To remind you, this is the prior of L and the prior of H. So this is the x ante expected cost. So it tells us that there exists a sequence of equilibria such that solicitations becomes indeed many are being solicited as the costs are made. The auctioneer solicits many bidders as the cost is made small. But the winning bid is almost surely this B upper bar that's smaller than the x ante expected cost. Now, I say exists in quotation marks because to really speak about existence, you have to speak about mixed solicitation strategies and then show that the mixed solicitation strategies are really not important. So, and I'm not doing all of this here. So I'm writing this existing, but for our purposes, it's really you can drop the quotation marks. So I'm not going, even this example is sort of hard to prove, so I'm not going to prove it fully. I'm just going to give you a few hints of what's going on here. So let us just guess a sequence of bidding strategies of this form, that bidders with signal above x hat bid some b upper bar, and bidders with signal below x hat bid some other bid that is smaller than b upper bar and bounded away. It might depend on k, but it's bounded away from b upper bar for all k. Now, these numbers are not arbitrary. We will have to choose them appropriately. But for now, focus on such a strategy. So everybody with a signal above x hat is bidding a certain bid. Everybody with a signal below x hat bidding a lower bid. And let us make a few observations here. So let's look at optimal solicitation given that the bidders behave in this way. So first of all, definitely this goes to infinity as s goes to 0, because you have these two bids and they are not converging to one another, they are bounded away. So of course there's always a probability for the auctioneer they will get everybody with a low signal and get a low bid. So if it's very low cost to get another bidder, they will go another bidder. So as s goes to 0, the solicitation increases without a bound. So this for sure. This is a key step. This is a very key step. What it tells you, this step, that we get this solicitation curse here, but this time that we saw in the example before, but this time it occurs endogenously. And this simply follows. We write the first, we ignore the integer problems, which we do not ignore in the paper, but here we ignore the integer problems, and write the marginal conditions of the auctioneer in both states, in state L and state H. Why is this the marginal condition? Notice in state L, for example, this is the probability with which everybody that the auctioneer will get, all the NL guys, will have signals below x hat, and they will make a low bid. This is the only case that another solicitation might be valuable, another bidder might be valuable. And then another bidder with this probability will get the high signal, and then the auctioneer will gain this. So this is the incremental value of additional bidder in state L when the auctioneer is already sampling NL. And marginal benefit at the optimum has to be equal to marginal cost. This is the marginal cost of sampling an additional bidder. And the same is true for the other state. So you just manipulate these two conditions. And you get that this implies necessarily that optimal solicitation has this form in the limit. And there's a slight other step which gives us this. So this is one key step. The important thing is, again, the calculation by which we get there, but the optimal solicitation creates a situation in which the bidder with the highest signal is more pessimistic than the prior. Just being the mere fact of being solicited, they're already more pessimistic than they would be just based on the prior. And this is the person with the highest signal. Now, another step here. Can we move my picture a little bit? Okay. Bidder, I want to argue that take the bidder with the highest signal, or the bidders with the highest signal, the expected value for them, conditional on winning at this B upper bar, the higher bid, is in the limit is approximately the expected value, expected ex ante value. And this is again a calculation, and the idea is that winning at B, remember that when you do make your expected, let me just say in words, when you do make your expected value calculations, you take into effect the count that you have been sampled. So this is what this NH over NL comes from. But if you bid at the atom, the probability of winning are somehow inversely proportional to these ends. So they cancel this out. And they also depend on, they're actually inversely proportional to n and to the likelihood ratio, to the inverse of the likelihood ratio at the top. So some cancellation occurs here, and necessarily a bidder who wins at the top gets a value that equal to expected, a bidder with the highest signal who wins at the top gets value, the expected value for them is equal to the ex ante expected value. So now we know how to construct our equilibrium. So for small s, the value of x conditional on winning at b, okay, sorry, we have one more step that we did also in the example. Consider now the possibility that the bidder with the highest signal overbids the atom. So conditional at winning, at overbidding and winning, the expected value, I want to argue, is lower than the ex ante expected value. And why this is so? It's just I do this simple calculation because now you win for sure. So this is your expected value if you overbid. And we said that this expression is smaller than 1 by step 2. So that means this whole thing is smaller than the ex ante expected value. So this is where this key step, step 2, comes in here. The calculation is if you overbid, you win for sure. So, so the value to you depends only on the prior, on the likelihood ratio coming from the signal, and the likelihood ratio from being solicited. There's nothing about winning because you win for sure. But step 2 implies that this expression is smaller than 1, which means this whole thing is smaller than the ex ante expected value. So now we can construct our equilibrium. We choose this B upper bar at the beginning was arbitrary. We choose it to be below the ex ante expected value and above this expression that we know is smaller than the ex ante expected value. And this is exactly what tells us that a bidder, this is exactly what gives us that a bidder with the highest signal who bids here gets expected value. We calculated they get this expected value, therefore the profit is non-negative because this is what they are paying if they are winning. And if they overbid, they get this expected value, therefore negative profit. So we obtained in this construction a similar situation to the situation that we had in the example. Of course, we are not done and have to check many other things. We have to verify that a bidder with a high signal does not benefit from bidding under B. We have to select this B lower bar appropriately, which I think I will not bother you with now. But the key steps were the following. Optimal sampling results in this necessarily in this inequality, which means optimal sampling necessarily in this environment leads to the bidder being pessimistic, more pessimistic than the prior. And therefore, the expected value, even for the highest signal of overbidding, is below the ex ante expected value. So this was one step. And the other key step was that for a bidder with the highest signal, necessarily winning at the atom is the expected value is approximately the ex ante expected value. So therefore, you can insert this equilibrium bid between these two, and it is possible to construct such an equilibrium. Now, notice I want to make a few remarks. The construction almost didn't use the fact that there are two effective signals. And it can be fairly straightforwardly extended to any finite number of effective signals. it would be harder to construct an equilibrium atom if the likelihood ratio is strictly increasing. But the main logic of the construction does not seem to depend on the discreteness of the signal, although we have not done so. Now, additional condition on the distribution that I presented to you and I just went is not really too demanding. So, now, what are the qualitative insights? When S is small, price is very likely to be upper bound in both states. It is lower than the X ante-expected value, so the auction does not become competitive, and there is no information aggregation because it prevails in both states. You can contrast it with ordinary common value auction. As the number of bidders becomes large, price becomes competitive and aggregates information well. I mean, if the likelihood ratio is large, and this follows from earlier work by Milgrom and Wilson. So in a common value auction, when the number of bidders becomes large, and if this is sufficiently large, information is aggregated well, and the auction becomes nearly competitive, whereas here in our world, it is not necessarily so. Now, there are other scenarios. I gave you one scenario with endogenous participation of the auctioneer soliciting bidders. You can think of other scenarios. Murto and Velimäki have a paper in which bidders get signals prior to costly participation decisions. So they first see a signal and then decide whether to enter. In a normal case, one would expect such scenario to have actually NH greater equal than NL. So therefore, the non-competitive, uninformative equilibrium of the sort we focused on here is unlikely, unless some perverse circumstances generate an entry curse of this sort, which I'm not sure is possible in the model. Now, there is an alternative. You can think about now a different story. There are different stories that there is an alternative opportunity whose desirability is correlated with the value in this market. And fewer potential bidders find out a lucrative alternative option in state L than in state H. So this may naturally lead to numbers of participants in state H being lower than state L. And the entry curves of the type we are talking about here without a decision being made by the auctioneer. So, so you would expect in such scenario to have the non-competitive, uninformative equilibrium of the sort that we focused on without the actions of an informed seller. And there is some equilibrium with this flavor in the paper by Atakan and Ekmeki. They have an equilibrium with this flavor. Now, to sum up, because I think I'm over my time, to sum up, what I want to say is this is not a model of an auction. I think of it as a model of a market. This is how I wanted to start my paper, and now I'm happy that I changed the change. So I wanted to start with a market, with entrepreneurs and investors, and show you an equilibrium in which simultaneously many entrepreneurs contact many investors, and show you this result that I showed you in the context of the single auction, show you this in the context of the market. And the reason I wanted to do it this way, because I think about it as a market model, not an auction model, as some phenomenon that can arise in markets with adverse selection, such as financial markets. I chose not to go this way because I thought it would be, I realized it would be too complicated, and I did what I did. And now I stop.
So any questions from the other room?
Continuity.
It's not discontinuity, because remember that I make this assumption. If you start with S equals 0 and some n, no matter how large, the auctioneer would like to bring everybody to the auction. If you increase S a little bit, the auctioneer would still want to bring everybody to the auction. Remember that I made here the assumption that when I make S small, I also make the number of, at the same time, the number of prospective, of potential, or the size of the market large. So the